Good morning, everyone.
Hello. I'll go ahead, Ruben.
Okay, I'll start. No worries. Um, Good morning, everyone, and thank you for joining us this Friday. It's Friday, yay, right? Um, so today's session for the Friday Math Happy Hour is to review the exam two. For those of you who are here for the Math 1324, please look at your chat. Go ahead and click on the link to go into um, that class. Yes? All right. So again, thank you for joining us, and we will get started. Please, if you have any questions, um, raise your hand or just go ahead and ask us or put us on the chat, and we'll get to your questions. So let's go ahead and begin. Um, so your exam 2 for Math 1314 is going to cover Chapter 2, and it's all of the sections from Chapter 2, right? So 2.1 through 2.6. So let's start with sections 2.6. And the reason we wanted to start with 2.6 is because 2.6 basically encapsulates everything, right? Everything from 2.1, 2.2, 2.3 in a nice little package. So we'll start with questions with our examples from 2.6. So let's first consider this rational function. F of x is equal to 1 over x plus 3. And what we want to do is A, state the domain of the function. B, identify all its intercepts. C, find the vertical and horizontal asymptotes. And D, plot or sketch the graph. Yes? So let's go ahead and start with A, state the domain of the function. So if we see that when we're looking at a rational function, what's going to restrict or what's going to limit our x values is the denominator of the function. And we never want the denominator of a function be equal to 0. So we ask ourselves, is there a value that we can put for x that's going to make that value 0? And hopefully we can see that if we put -3 for x, -3 plus 3 will give us 0. Hence, if we try to put this in our calculator, it's going to give us an error, right? This is undefined. So the domain, the restriction for this function is um, all real numbers except for x equals -3. So the solution would be that last one, right? Um, and we will circle this. Again, I talk and I should follow my slides, and everything is information here, right? So if we didn't see it, we can use algebra to find that value set. X plus 3 equals to 0, and we solve for x. Subtract 3 on both sides. 0 minus 3 is -3. So x equals -3. So we see that our solution, okay, would be this last one, okay? All right. Again, if you have any questions, please let me know. Let's look at B, identify all the intercepts. So let's start with the x-intercept. So to find the x-intercept, we're going to set y equal to 0, right? So we know that f of x, that name is replacing the y. So we can go ahead and substitute f of x for the 0. So 0 is equal to 1 over x plus 3. So again, we want to solve for x, and the first thing we would do is we would multiply both sides by x plus 3. And when we do that, okay, of course, the x plus 3 divided by x plus 3 becomes 1. Most of our students just say that it cancels, right? But the other side, when I multiply x plus 3 times 0, that gives me 0. And we end up with 0 is equal to 1. And this is a false statement. 0 is not equal to 1. So hence, since this is a false statement, there are no x-intercepts. And what you would put on the computer would be does not exist, DNE, right? Well, let's look at the y-intercepts. To find the y-intercepts, we're going to set x equal to 0 and then solve for y. So everywhere we see x, we're going to plug in 0. So we have 1 over 0 plus 3. So 0 plus 3, and if we simplify, it's just going to give us 3. So we end up with 1 over 3. So our y-intercept in point format, when x is equal to 0, y is equal to 1/3. That is our y-intercept point. Um, Now let's look at C. Find any vertical and horizontal asymptotes. Um, so let's start with steps to find our vertical asymptote. We see that the vertical asymptote, if we factor out our numerator and denominator completely and cancel like terms, okay, we're going to be left with only the vertical asymptote. So it's very important that we do this step before we start just looking at the denominator to see if we can factor both the numerator and denominator. Um, and the step 2 is set the denominator equal to 0 and solve. This is going to, if we find any restrictions after we've simplified, if we find any restrictions, those restrictions end up to being intercepts, sorry, excuse me, asymptotes, vertical asymptotes. So let's go ahead and look at our problem again, our example again. So 1 is already simplified, so there's nothing for us to factor. And x plus 3 is already in its simplest form as well. So we can skip step 1 and move on to the step 2. Set the denominator equal to 0 and solve for the variable. And again, we had done this already when when we're trying to discover the domain. So when we solve for this, we saw that x is equal to -3. So if you can see this, solving for the domain on a rational function, you also are solving for the vertical asymptote. Those restrictions that that function is going to have equals to or represents these vertical asymptotes, these imaginary vertical lines that the graph does not cross or touch. So the equation of our vertical asymptote is x equals -3. All right, now let's move to, and if we graph this, again, on our graphs, we graph this as a dashed line. Again, these are dots, but this is a dashed line, okay? So at x equals -3, we have an imaginary vertical line that our graph will not cross or touch. All right, now let's look at the other part, the horizontal asymptote. So for horizontal asymptotes, we have several cases. We have 3 cases that will determine what if we have a horizontal asymptote. So let's review this really quickly. Um, if the degree of the numerator is smaller than the degree of the denominator, then there is a horizontal asymptote that exists at y equals 0. Okay, this is for any rational function that has this going on. The numerator's degree is smaller than the degree of the denominator. Case 2 or situation 2 is if the degree of the numerator is equal to the degree of the denominator, then we have a ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. This will be our horizontal asymptote. It's a fraction or ratio, okay? And then the third case, if the degree of the numerator is larger than the degree of the denominator, then there exists no horizontal asymptote, okay? But the case 3 is a little special. It may not have a horizontal asymptote, but what it's going to have is going to have a slant asymptote. And we wrote that in red, okay? So let's go back to our problem. And we see that if just to help you out, let me write the numerator a little bit different, okay, or this problem. If I do this, x to the 0 power, anything to the 0 power is going to give me 1. That's what this one is. And the bottom one, let me rewrite it as x plus 3. But here, we don't write the exponent. The exponent is 1. We already assume if we don't see an exponent, that exponent is 1. So in this case, you see that the degree of the numerator is 0, and the degree of the denominator is 1. Hence, the degree of the numerator is smaller than the degree of the denominator. So we are going to have a horizontal asymptote at y equals 0 for our problem. Okay, so this is our horizontal asymptote, y equals 0. And again, we represent asymptotes as these imaginary lines as dashed lines on our graph. Okay, so at y equals 0 is represented by this blue one. Okay, all right. So we have these two things. Let's go ahead and continue. Let's find our y-intercept. Well, we found our x-intercept. We found our y-intercept. We have our vertical asymptote. We have our horizontal asymptote. So they're asking us to graph this function. So let's plot some additional points to help us. Okay. So let's go ahead and look at what we have first. First, we have our y-intercept here. When x is equal to 0, y is equal to 1/3. It had no x-intercepts. We have a vertical asymptote at x equals -3. We have a horizontal asymptote at y equals 0. So for me, what I like to do is I like to pick some points that are either to the left or right of my asymptotes, right? So here I'm going to pick just this -2. When x is equal to -2, what is my y value? My y value is 1. When x is equal to 2, my y value is 1/5. Let's just pick some additional more points. When x is equal to -4, now it's on the left side of my asymptote. I have y equals -1. And when x is equal to -5, y is equal to -1/2. Okay, so plotting these additional points, it gives me this. And again, because I know the parent function of this graph, I know more or less the behavior of this graph, right? So again, this is nicely written, right? We did, the computer let us connect the points, but we see that our line will come very close to our asymptotes, will not cross or touch them, and it will cross these points. Again, it's not going to cross my horizontal asymptote. It's going to get very, very close. And then same thing with the bottom. I tried to connect the points. It's very close to my horizontal asymptote. It's not going to cross it or touch it, and then it's going to come close to my vertical asymptote, and again, it's going to get very close to it. It's not going to cross it or touch it. And again, this, when we do it by hand, it gives us a really good idea, because when we're selecting the correct choice on the computer, it's very obvious to see once we have all this information down. Okay, all right, so let's look at another example. Let's look at this one. It's a little bit more complicated. We have c of x is equal to 3x plus 2 divided by x plus 3. And we're going to answer the same questions, state the domain, identify the intercepts, find the vertical asymptotes, and plot additional points. And I gave the answers already for the x and y. No worries. Okay, so let's look at the first. Let's look at A. Again, to find the domain, let's set the denominator equal to 0. That's what's going to give us any restrictions. All right, so when we set the denominator equal to 0, we have x plus 3 is equal to 0. We solve for x is equal to -3. So we see that our domain is all real numbers except for x equals -3, right? And again, hint, hint, we've also found our vertical asymptote. This restriction translates to our vertical asymptote. So to answer the first part, again, it's going to be the second one, right? All real numbers for x except when x is equal to -3. All right, so let's find our intercepts. To find our x-intercept, we're going to set y equal to 0. So we go ahead and do that. 0 is equal to 3x plus 2 divided by x plus 3. Let's multiply by x plus 3 on both sides. And this is going to give us 0 is equal to 3x plus 2. I'm going to subtract 2 on both sides. It's going to give me -2 is equal to 3x. And then I'm going to divide by 3 on both sides. So x is equal to a -2/3. This is my x-intercept. Now let's find our y-intercept. Let's set x equal to 0 and solve for y. So everywhere I see x, I'm going to plug in a 0. So we have 3 times 0 plus 2 divided by 0 plus 3. We do simplify. 3 times 0 is 0, 0 plus 2 is 2, and 0 plus 3 is 3. So our y-intercept, that should be a y equals 2/3, okay? All right, so we already found our vertical asymptote when we were solving for the domain of the function, and we saw that it was x equals -3. This is our vertical asymptote. Now, let's look at our horizontal asymptote. We had 3 cases, okay? Again, this is the graph. It's a vertical line, and we represent it as a dashed line. So the horizontal asymptote we see here, the degree of the numerator here is a 1. We don't write it, and the degree of the denominator is also a 1. So since these two are equal, the degree of my numerator is equal to the degree of my denominator, we're going to have a ratio. Our ratio is going to be the division of the leading coefficient of the numerator, which is 3, divided by the leading coefficient of my denominator, which is 1. So 3 divided by 1 is 3. So my horizontal asymptote is y equals 3. All right, so let's just plot additional points to get a better look of this graph. So again, we're going to pick a few points. We're going to do x equals -2, x equals 2, x equals -4, x equals -5, which is very similar to our previous problem. Again, so when x is equal to -2, y is equal to -4. When x is equal to 2, y is equal to 8/5. When x is equal to -4, y equals 10. And when x is equal to -5, y equals 13/2. Okay? So we plot these points. Again, we're going to do a little bit of cheating and use the computer to graph these points. We get these move curves that, again, they come close to our asymptotes, but will never cross or touch these imaginary vertical and horizontal lines. Okay? All right. Let's do one more. Let's consider this rational function, x squared minus 9 divided by x. Again, we can simplify the top. The top can be simplified or factored out. I see that's a difference of squares, but the bottom is just x is already simplified. So even though we can factor out the top, it's not going to help us simplify. Okay, so let's set the denominator equal to 0. So this one's easy. If we set the denominator equal to 0, x is equal to 0. So our answer is all real numbers except for x equals 0. That is our domain, right? But again, what we just found was our vertical asymptote. We have a vertical asymptote at x equals 0. Okay. Now let's go ahead and find the intercepts. To find the x-intercepts, set y equals to 0. And when we do this, we have 0 is equal to x squared minus 9. Again, you can use the square root property, or you can factor it, or just solve. So add 9 on both sides. We have 9 is equal to x squared. Take the square root of both sides. And again, the square root of 9 is going to be plus or minus 3. Yes? So these are the intercepts. So to find our y-intercept, we set x equal to 0. Everywhere we see x, we're going to plug in 0. So we have 0 squared divided by 9. But we have a 0 in the denominator. What is our calculator going to tell us? And we had to evaluate this, right? Because we're going to end up with -9 divided by 0. Well, we're going to get an error. So hence, since this does not exist, we have no y-intercepts for this problem. Okay, so again, I spoke about this, but when you're finding the vertical asymptotes, you always want to factor out both the numerator and denominator to see if anything cancels. And again, I saw that this is the difference of squares. I am just with x minus 3 and x plus 3. Nothing cancels. So again, my only vertical asymptote is x equals 0. All right, my horizontal asymptote. The degree of the numerator on this one is 2, and the degree of the denominator is 1. Since my degree of my numerator is larger than the degree of my denominator, I have no horizontal asymptote. Okay, but I do have a slant asymptote on this one. Okay, so what we have again is a slant asymptote, and to solve for this, what I like to do is like to do division, and that's why we cover division, because this is going to give us the equation of our slant asymptote. So if I do synthetic division to solve for this, again, I said I have a quadratic as a numerator. So if I'm going to do division, I have to have a placement value for all my values. And if you see, I'm missing my x term. So since I'm missing my x term, I'm going to represent that as 0. So we have 1, 0, and my constant is -9. So let's go ahead and do the synthetic division. Bring down my 1. 0 times 1 is 0. 0 plus 0 is 0. And 0 times a -9 is a -9. So hence, my slant asymptote for this equation is just y equals x. Okay, so this is my quotient. My quotient is just the x. Again, I started with a quadratic. So my first term is a linear, right? It's just the 1. So I have the x equals 1. I don't have a constant, and this is my remainder, but I'm not interested in my remainder. I'm just interested in my first part of my quotient. So again, the slant asymptote for this is going to be y equals x. Okay, let's go ahead and plot some additional points to see what the graph of this looks like. So again, this is my slant line at y equals x when It's just basically when the slope is 1, right? 1 over 1. Rise 1, run 1. All right. So my additional points again, I did 2, 4, -2, and -4. I ended up with these points. I'm going to go ahead and plot them. And then what I'll do is I'll let the computer do the nice work of joining those points together, and we get this graph. Again, these dots um, come very, very close to our graph and to our asymptotes, but they never cross or touch, okay? Both on the bottom and the right. Again, we can't see it, but again, we have a vertical asymptote at x equals 0. At our origin, we have this imaginary vertical line. Okay? All right, so let's look at another example. Write the quadratic function in standard form. Identify the vertex and the axis of symmetry. Okay, so there's several ways of doing this. So let's do it. I like to do this method, and to find the standard form of the quadratic equation, because this is right now it's in general form, right? What I like to do is it's a process called completing the square. So the first thing that I'm going to do is factor out a 2 from the first two terms because I want the leading coefficient to be a 1. Okay, so I'll factor out a 2, and this gives me 2 times x squared plus 4x. And I left a blank here because, again, I'm going to complete the square, okay? I have plus 7. So the process to completing the square is I'm going to take half of b and then square it, okay? So if this is a, this is b, so b is my 4. So I'm going to take half of 4. 4 divided by 2 is 2, and 2 squared is 4. So for this to be a perfect square, I need to have a positive 4. So I can't just add that positive 4 just because I feel like it. Even though I'm the teacher, it's like I can't unbalance an equation. I always have to balance everything. So if I want to add a plus 4, um, if I add a 4 and minus 4, what is the value that I'm adding? 0, right? 4 minus 4 is 0. So technically, I'm not altering the problem. I'm not adding anything extra because I'm adding 0. And when I add zeros, I'm not adding anything to it, right? But I'm going to do a little bit of math manipulation, right? I want to use that positive 4 to complete my square. So when I move the parentheses here, x squared plus 4x plus 4, when I take this negative 4 out of the parentheses, I gotta give back the 2 that had been taken away from the beginning. So 2 times the negative 4 gives me a negative 8. Now I can put it outside my parentheses, and um, and I can do a little simplifying. Negative 8 plus 7 is going to give me a negative 1. And this inner part that I have here, x squared plus 4x plus 4, is a perfect square. Hence, that's why it's called completing the square, because we make a perfect square. We have this translates to x plus 2 times x plus 2. But then you're wondering, how do I know that? How do I know that x squared plus 4x plus 4 becomes x plus 2 times x plus 2? Well, I go back into my process on how to complete the score. I saw that that number that got squared before I completed it was a 2, right? 4 divided by 2 squared gave me that 4. So before it became a square, I had a value 2. And that is the clue that tells me that that's what this value is here, the 2. Now, why do I know it's positive? I look at the sign in front of the b. Since this is positive, I know that both of these have to be positives, right? The x plus 2 times x plus 2. All right, so if we simplify this, we have 2 times x plus 2 squared minus 1. Voila! We converted our general form quadratic into what's called standard form or vertex form. And we like this form because just by looking at it, we can see what that vertex is. Since we have a plus 2, this graph got shifted 2 units to the left, 1 unit down. So my vertex is -2, -1. Okay? And the axis of symmetry is equal to x negative 2. Our axis of symmetry will always be the x value of our vertex. Okay? All right. So let me go ahead and have Ms. Chuka take over for the other half. Okay? Thank you.
Thank you, Mr. Carizales. So let's go to the next example. So it says find all the real zeros and determine the multiplicity of each zero. Okay, so we have this should be f of t is equal to t to the fourth minus t cubed minus 30t squared. So as Mr. Carizales mentioned, there's different ways to solving this. And so for this example, we're going to go ahead and factor out a t squared since that is common to all three terms. And so here I have another mistake. So let's just ignore the bold one, but let's go with, or let me check really. Okay, actually, so the bold one is going to be okay. And let me just cross out something here really quick with my pen. So I'm going to erase this here. And so this up here is okay. So if you notice here, the terms f of t is equal to t to the fourth minus t cubed minus 30t squared. They all have at least a t squared in common. So we can factor out a t squared, resulting in t squared minus t minus 30. So from there, we can look at each factor completely. So the t squared minus t minus 30, we can factor as t minus 6 times t plus 5. So we can set each factor equal to 0, as we have here, and then solve for each of those factors. So for 0 equals t squared, we can take the square root, giving us t equals 0. And then for t minus 6, if we add a 6, we get t equals 6. And for t plus 5, we will get t equals negative 5. So the question wants to know the multiplicity of each 0. So multiplicity, remember, just means how many times does a 0 appear. So if we look at t equals negative 5, we can see that this negative 5 is only occurring one time. And the number 1 is an odd occurrence. And so therefore at t equals negative 5, the graph is going to be crossing. And then at t equals 6, 6 only appears one time. And so it has an odd multiplicity, which means that the graph will also cross. And at t equals 0, we can just see that we have t equals 0 that looks like it appears once. But if you notice, your t squared is telling us that t equals 0 actually appears twice. Since it appears twice, that's an even multiplicity. And so the graph is going to touch and turn at that point. Okay, so we'll look at some more examples here in a second. Just if you're interested in the graph, if you notice here, it crosses at this point, it crosses at this point, but then it's going to touch at the t equals 0 and then turn. So one of the things that was done, and I think it was in section 2.2 or 2.3, was the end behavior of a polynomial. And so I always like to tell my students, if you remember these four graphs, and we've been working with these graphs throughout chapter 1 and chapter 2, then you can always remember the behavior. So for x squared, this always behaves, it rises to the left, rises to the right. A negative x squared falls to the left, falls to the right. And then the x cubed rises right, falls left. And negative x cubed rises left, falls right. So to do the end behavior, you are going to be looking at the degree. So if the degree is even, as it is in the first two examples, then the graph is going to behave like one of these. The difference is in the leading coefficient. If it's positive, then it's going to behave like this graph. If it's negative, then it's going to behave like negative x squared. And the same over here, the degree, if it's odd, then it's going to have similar behavior as this. And then the leading coefficient will determine if it rises right or if it rises left and so on. So if we look at this example, describe the left hand and right hand behavior. First, we need to identify the degree. So the degree is 3, which is odd. So that means that it's going to behave like this one or like this one. So then we look at the leading coefficient. In this case, it's positive 12. So that means that the behavior will be like this graph of x cubed. So in our answers, we would say that the graph rises right and falls left. Again, if you have any questions, please put it in the chat or raise your hand. That way we can address those questions. For multiplicity, we did an example. So again, with these two graphs, you can easily remember what the multiplicity will be. So for x squared, the 0 is at x equals 0, but it appears twice, so that therefore it touches and turns. At x cubed, the 0 is 0, but it's going to appear 3 times. And since 3 is odd, that means that the graph is going to cross, and then it's going to keep going. Okay, so the graph crosses. Now, another thing that we did in section 2.5 was the possible rational zero theorem test. And this test was used to help us find a list of possible zeros. And so in order to find that list of possible zeros, we were going to look at the factors of the constant term, which is your constant, and then the factors of the leading coefficient. In this case, the leading coefficient is always in front of your variable with the highest degree or the highest exponent. And we were able to use this theorem to help us do problems like this one. Find the rational zeros of the polynomial function f of x equals x cubed plus x squared minus 9x minus 9. Since this has 4 terms, you can try to factor by grouping, but if that doesn't work, then, or if you're not familiar with factoring by grouping, then we can go to use the rational zero test. So my constant here is -9, and the factors of 9 are 1, 3, and 9. So these are all the numbers you can multiply to give you a 9. But we're going to include the negative as well in there. You'll see that in a second. And then your coefficient of x cubed is 1, so we only have the factor of 1. So I can write my factors as plus or minus 1, plus or minus 3, plus or minus 9, divided by plus or minus 1. So if I divide these, 1 divided by 1 is 1, 3 divided by 1 is 3, and 9 divided by 1 is 9. We want to enter the smallest first, and then the positive ones. So this is our list of possible zeros. That means that from this list, we might have a 0. So to find it, we can use synthetic division. So I'm going to try 1. So I list my coefficients here, bring down the 1, multiply it times 1, so we get 1 plus 1 is 2. 1 times 2 is 2, plus -9 is -7. And I did not get remainder of 0, so that means that 1 is not a 0. So we try a -1. So we do the same process. Oops. So we do the same process. We bring our number down, times -1, we get 0. 0 times -1 is 0, plus -9 is -9. And so here we end up with 0. So that makes us happy because we found at least 1 0. But more importantly, if we write the quotient down, we get x squared minus 9. And since it's quadratic, we can either factor, use a quadratic formula, square root property, any of the quadratic methods. In this case, we're going to use the square root property by adding 9 on both sides and then taking the square root. So x is equal to plus or minus 3. So those are our zeros. So let's go ahead and list our zeros here. So we have x equals -1, x equals -3, and x equals 3. And if you want to know the factors, then that's x plus 1, x plus 3, and x minus 3. Okay, so let's try the next one. So I'm going to give you like about 40 seconds to try to find your possible zeros. And in the meantime, while you try to find them, I'm going to get my charger because my laptop is running out of juice. So let me just get my charger. So to find your possible zeros of f, let me go ahead and connect myself. Okay, so again, there's different ways you can solve this problem. If you wanted to, you didn't have to find the possible rational zeros. You could have maybe factored out an x squared from here and go that way. Yeah. So, but here, the possible zeros, remember you have to look at the constant, but we don't have a constant. So the factors, well, we have a constant, which is 0, right? So the factors of 0 is just going to be 0. And if you divide it by the factors of the leading coefficient of 1, well, you still get 0. So that is why I'm choosing 0 to test it. So we're going to bring down the 1. 0 times 1 is 0. And if we do the process, then we get negative 1 times 0 is 0, and so on. Okay. Remember, I have two zeros over here because I don't have a next term and I don't have a constant. So if I get my coefficient or my quotient, then we get x cubed. So we start with this 1, but it's 1 degree less. So we're going to have x cubed minus x squared minus 6x. So this is still not quadratic. So we can repeat the process. So your constant for this quotient is still 0. So if we test it, we bring down the 1 and then we keep going. So we get 1, negative 6, and 0. So the quotient for that, since we had x cubed, now we're going to start with x squared minus x minus 6. Finally, it's quadratic. So now we can use quadratic methods. And in this case, I chose to use the quadratic formula. You can factor, but maybe I was going to give you a different example here. So b is negative 1. So we plug in those numbers and simplify. We can see that our two zeros are x equals 3 and x equals negative 2. Again, if you prefer to factor, then you can factor. So we should have 4 zeros. So let's see what our 4 zeros are. So we have x equals 0 from the first synthetic division, x equals 0 from the second synthetic division, and x equals negative 2 and x equals 3. So the multiplicity of 0 is 2, so the graph is going to touch and turn. The multiplicity of negative 2 is odd, so the graph is going to cross, and then it's also going to cross at x equals 3. The maximum number of turning points can be found by taking the degree and subtracting 1, so the degree minus 1. So in this case, we should have at most 3 turning points. So let's take all of this information that we just got, because remember, if we go back to the original question, it wanted us to sketch the graph at the very end. So let me go back. So whenever I sketch the graph, I like to plot my points, okay? And then I like to apply the end behavior. So since this is even, we know that the behavior is either going to rise on both directions or fall in both directions. In this case, it's positive. So that means that it's rising on the left and it's rising on the right. At x equals 3, we said that the graph was going to cross. So I like to draw a line through it. And then at x equals negative 2, it's also going to cross. Now for 0, I know it's going to touch, but I need to know what else is happening with my graph. So in that situation, we want to plot some extra points. Okay, so let's plot some extra points here. And I chose negative 1 so I can see what's happening here. And then I chose positive 1 and positive 2. So if we input negative 1 and for all the x's here, we get negative 4. So at f negative 1, we get negative 4. And then if I plug in a 1 everywhere, I get a negative 6. So that's right here. And then for negative 16, for 2, I get a negative 16, which is all the way down here. So if I connect my dots here, the graph is going to come down. It's going to go to 0. And I know that at 0, it's going to touch and turn. Then it's going to come back down. And then it's going to go back up. Okay, so that is my sketch of my graph. And a prettier version from decimals looks like this. Okay. But by, like Mr. Carizales said, by doing it by hand, some of your questions on WebAssign is multiple choice. So then you can take your graph and see which graph is going to be your answer. Okay. So one of the other things that we did, this is towards 2.5, I think, in section 2.5. It says find the polynomial of a real function, and they give you the degree, and they give you the zeros, and they give you a solution point. And our goal is to find the actual function. And so first, let's talk about the zeros. Since I have degree 4, I should have 4 zeros, but I'm only given 3. So what is the missing 0 here? I should have another one. Did I make a mistake, or is there a missing number that, what should it be? Any guesses? So remember, if you have complex numbers, they come out in pairs, right? So here, since I have a complex number of I, then we're going to be, its conjugate is also going to be imaginary. So here we should have our fourth zero is going to be x equals negative I. So once you have your zeros here, then you want to get the factors. So to get the factors, we're going to put everything on the same side. So negative 4, if I bring it to the left side, I'm adding 4 on both sides. And then for x equals 1, we get x minus 1. For x equals I, we get x minus I. And for x equals negative I, we get x plus I. So we take our factors. I know it's going to be a polynomial, so I'm going to have a leading coefficient, which I don't know what it is yet. And then I'm going to list my factors. Okay. So I personally like to multiply the imaginary numbers first. So x times x is x squared, x times I is ix, negative ix is negative ix, and then negative I times I is negative I squared. And what do we know about I squared? Okay, so I squared is just going to be, well, let me simplify here. X squared, the ix and the negative ix become 0. So we end up with x squared minus I squared. And so as you saw in the chat, I squared is the same as negative 1. So I can replace that there. So if we simplify some more, then we end up with negative negative is positive 1. So now we just have 3 factors left. So we just multiply. Okay, so I'm going to multiply x minus 1 times x squared plus 1. And we end up with x cubed plus x minus x squared minus 1. There's nothing for me to simplify here. So I keep multiplying. So now it's going to get a little bit longer, right? But x times x cubed is x to the 4th. X times x is x squared. X times negative x squared is negative x cubed. X times negative 1 is negative x. And then we start with the 4. So 4 times x cubed, 4 times x, 4 times negative x squared, and then 4 times negative 1. So once we have all of this multiplied out, we can combine our like terms. And so we're going to end up with x to the 4th plus 3x cubed minus 3x squared plus 3x minus 4. So all that we're missing is to know what this an is. Okay. So if we look at our solution point, f of 0 is equal to negative 8. Well, what do we know about 0? Is this going to be our x coordinate or our y value? Okay, so that number in there is going to be our x. And then if we input x, we get negative 8. Okay, so I'm going to set this up as negative 8 is equal to my leading coefficient. And anywhere I see an x, I'm going to replace it with 0. So I have all these are zeros since I have all x's here. And if I simplify, I end up with an times negative 4. And if I divide by negative 4, then I get 2 is equal to an. So they're telling me here that my leading coefficient is 2. So I can plug that back in. But now I need to simplify. So I'm going to multiply by 2 into the parentheses. And so this polynomial function is going to be 2x to the 4th plus 6x cubed minus 6x squared plus 6x minus 8. Okay, so this is going to be our final answer down here. So if you were to apply, if you were to find the zeros for this function, then you're going to end up with these zeros here. Any questions on that one? All right, so we have one more that is similar. Okay, it says use the given zero to find all the zeros. So we want to find all the zeros. And they tell you that 4 plus 2i is a 0. So this should have 3 zeros, right? So automatically, can anybody tell me what another 0 is just by knowing that 4 plus 2i is a 0? So it's conjugate, right? So the conjugate 4 minus 2i is also going to be a 0. And so we'll look at that in a second. So to find the zeros, I can use that here to use synthetic division. So x cubed is 1, x squared is negative 12, x is 52, and my constant is negative 80. So I'm going to bring the 1 down, and then I'm going to multiply 4 plus 2i times 1. So 4 times 1 is 4, and 2i times 1 is 2i. So I put that result in here. In order to add it to negative 12, I can only add the real part. So negative 12 plus 4 is negative 8 plus 2i. Okay. So now I have to multiply. So I'm going to multiply 4 plus 2i times negative 8 plus 2i. So 4 times negative 8, negative 32. 4 times 2i is 8i. 2i times negative 8 is going to be negative 16i. And so I'm going to get this stuff here, right? 2i times 2i is 4i squared. So it looks like it's getting crazy, but it's actually going to be really nice once we simplify. So let's simplify a little bit. Let me go back here. What do we know again about I squared? I squared is the same as negative 1. So negative 1 times 4 is negative 4, plus a negative 32 gives me a negative 36. So this should have been negative 36. Or I haven't combined it, so that's okay. Let me go back. So I combined it. 8i minus 16i is negative 8i. And now negative 32 minus 4 is negative 36 minus 8i. If I add the 52 to the negative 36, I get 16 minus 8i. Okay, so we do the multiplication again. 4 times 16, 4 times 8i, 2i times 16, 2i times 8i squared. So we end up with this. Notice here negative 32i plus 32i is going to become 0. And negative 16 times a negative 1 will become a positive 16. Okay, so if we simplify, then we're going to end up with 80. And so negative 80 plus 80 is 0. And I know I should have gotten a 0 here because they told me that this was a 0. If you don't get a 0 here, then we did something wrong in our multiplication or addition. So our next step is the quotient, right? So I have a 1, so that's going to be my x squared. This is going to be my coefficient for my x term, and then this is my constant. So this is quadratic, so I could use quadratic methods, maybe the quadratic formula, but this looks kind of crazy because I have i's in there, but it's okay. I encourage you to try it and have some fun, right? But what we could use is we can use the synthetic division again. But this time, I'm going to use the conjugate of 4 plus 2i. I'm going to use 4 minus 2i. So here's my coefficients. Bring down the 1, multiply times 4 minus 2i. So negative 8 plus 4 is negative 4. My i's cancel. And then multiply again. So we get negative 16 plus 8i. So we get a 0. So my quotient now is x minus 4. And I can set my quotient equal to 0. And so I get x equals 4. So my three zeros are x equals 4, 4 plus 2i, and 4 minus 2i. Okay, so that is going to be our this 0 should be a 4. Okay, so just cross that out, put a 4. But so your test is this week. Some of you maybe are going to take it over the weekend. Maybe some of you will take it next week. So everybody is at different places, right, depending on your instructors. But we do wish you the best on your tests. And I'm going to go ahead and pass it over so that they can show you what's coming up for our next Friday Happy Math Hour. And so thank you everybody for joining us and have a great weekend.
Thank you, Ms. Chuka. Thank you, everybody, for being here today. Please join us next Friday at 11 a.m. for our next session of the Happy Math Hour. We'll be covering exponential and logarithmic functions or system of equations. We do want to remind you all about our previously recorded sessions, which are available on the YouTube playlist. We now have the TVEs updated each week on YouTube, and I'll be sharing that link with you. And this session will also be available on this playlist later today. Please know that our online tutoring is open right now and available through Blackboard Collaborate Ultra 7 days a week with our new hours for online tutoring from 12 p.m. to 9 p.m. Monday through Sunday, and face-to-face tutoring is still available Monday through Friday, 8 a.m. to 5. Thank you so much, Ms. Chuka, Mr. Carizales, Mr. Isasi, for presenting today. Thank you too to our audience for coming and being a wonderful audience, and we hope to see you next week. Bye, everybody.